Okay, we get started. So last time we considered the following objects. Say U V1. V1 is the incompressible flows, tangent to the boundary such that the vorticity is in L2. In fact, it is different from H2, H1. Yes, it is, I don't know, a little stronger. In fact, in this space, the dynamics is not well defined. Not, no, at least we don't know if it is well defined. So there is some subspace which is called geodesic space. Such that curl U have infinity. Yeah. So in this space, there is good dynamics, means that there exists unique, slightly generalized solution of Euler, which is defined for all t, for all time. So no, they in fact, y is invariant under the dynamics, and all our reasonings are good in the space y. Yes. Now, so from now on, we assume that U in the Udovich space. Now we introduced the set E is the set of mixing operators. Yes, and now we introduce omega U equal the set of V such that less than U and V less than U is the same as curl V equals K curl U K some operator, some mixing. Yeah, so it is V is less than U if vorticity of V is more mixed than vorticity U, more diffuse. Now, of course, any mixing always works in the space at infinity, and but it is maybe more convenient to measure to keep considering L2 norm of vorticity. Yes, but keeping in mind that we are working in a little stronger space, Udovich space. And we consider omega U is this set, and such that energy of U V equals energy of U and energy of B U is simply 1/2 ln U into square. Yeah, so it is a kinetic energy. And that's it. And now, given U Euclidean space, we define orbit of U equals, let's say, of U C. No, the solution of Euler equation. The initial condition U orbit U. So that we define, and we look for minimal elements of omega U. Yeah. So if it is, we have here partial order, so we can look for a minimal element, and we know that such elements exist by the zone lemma, and that if V is minimal element of omega U, then V is a stationary solution of the Euler equations, and there exists functions f such that V satisfies omega equal delta psi equals f psi, where V is the skew gradient of psi, omega is delta psi is curl V. Yeah. No, I repeat what was last time. And so there exists, no, in particular, every such, okay, we have what we have. And there are some classification that some flows are energy deficient, some other energy excessive, and some other, and one more, only one up to constant flow is flow with constant vorticity. And for some time, there was a conjecture that if we run the Euler equation started from some initial condition U, then the vorticity will be mixed irreversibly, and as t goes to infinity, the vorticity will weakly tend to some limit, and no, at least yes, weakly tend some limit, and this limit will be vorticity of some minimal flows. Such flows, minimal elements, I call them minimal flows. So that minimal flows are the sort of attractor of Euler equation. And it was a surprise that when I ran some numerical simulations, I found that no, it is wrong. And I found some other people who ran such simulations. Now it is not so difficult. And it is, I would say, uh, uh, stable fact. Yes, that if you start from whatever initial condition, usually we don't reach the solution doesn't reach the stationary state, and it is variable in time. Yes. So we have to look closer what it is. Unfortunately, I have lost all my pictures and movies. It was some time ago, so I cannot demonstrate you the real movie, how it looks. But you can find them in internet. There are many of them. No, in different contexts. For example, we can consider the flow which is stirred by some small random perturbations, random forces, yes, and which are counteracted by small scale viscosity. And then we'll see appearance of also some stable, robust structures. Yes, no, usually if we are working on the torus, we can see two big vortices with opposite signs, which are moving around, and at the same time they are breathing, they change their shapes, so we have such a funny exchange of them. Sometimes we have a different picture. We have not more vortex. For example, we have more vortex. I don't know. This word can be either sine or say minus. Yes. Then these vortices are moving even more interesting way and definitely non-periodic. To some degree it looks like quasi-periodic, but it is not sure. Yes, if you change a little bit, increase your resolution, then you can see that inside of this vortex, you have two small vortices and so on. So we can see the hierarchy of such vortices. And all this picture is, I'm not sure that the result will be quasi-periodic. Maybe for different configurations, it may be, say, chaotic in some sense, hyperbolic dynamics. I am not sure. It is all terra incognita. Other thing which is looks quite bizarre is the following. What happens in the background? It looks very close to constant. Yes, and there is interesting possibility that in the final state, when everything is done, it is really constant. So we have coexistence of constant background, I mean constant vorticity background, and some number, maybe infinite number of these finite size vortices. And it looks like, no, of course, what it is like. It is like solitons. Yes, so we see like solitons for Euler equations, and it looks like there appears some attractor. No, I would say very strange attractor in the phase space, in the space, no, in this case, just in the Udovich space, there exists some attractor in this weak sense. So it is attractor in the sense of velocities, but not in the sense of vorticity, of course. Uh, uh, for vortices, maybe it is weak attractor. That's it. No, if I have in the end more time, I would say ruminate about these things a little further. But now, what can we say? So for now, let us forget about this hypothesis that these minimal flows form through global attractor. It is wrong. And what can be said next about this would be attractor?
Excuse me, I have a question. So, do I understand correctly that the final state does not have to be a stationary solution of Euler, or you are not saying this?
It is not stationary solution of Euler. Yes, it is very interesting. Yeah. By the way, this all this theory proposes interesting way how to find solution of this equation. Yes, let us take arbitrary u, arbitrary initial velocity with the initial Cartesian string function. Yes, and start mixing them by hand. Yes, no, how to do it? It depends only on our fantasy. For example, we can pick a small piece here randomly and mix them. Yes, if the energy changes, then we try to find other pair such that the energy changes in opposite directions so that they can compensate one another. Then we repeat it again and again. Yes, and in the limit, what will be in the limit? So after I tried it by numerically by computer, it turned out that it really converged to some function psi which satisfies this equation, or omega. Better I work with omega. So omega which satisfies this equation. So psi is inverse Laplacian of omega. So omega is f of delta minus 1. This equation. Yes, it looks quite funny, especially if you draw the diagram where here is omega, here is psi. Yes, we have, we divide our domain into many cells, each cell represented by a point. So initially we have some cloud of points here, and then this cloud starts aligning along some curve. Yes, after all, we have something like this. All these points tend here.
Yes, unmixing.
Yes. It looks like there are fleas which are jumping here and jump and closer to this curve. What is this curve? And again, it depends on the way how you mix vorticity. Yes. Okay. Okay. Now let us go further. So we have omega of u is or omega of u is orbit of u. Omega bar of u with closure. Why weak? With closure of omega of u in Eudovic space. With closure. And for any v in O bar of u, we have that non curve v into less we call non curve u L2. Yes, so because after all it get mixed. And now I give the basic definition. V in V is a generalized minimal flow was linear flows if for any W the following is true. Now W equals norm V in L2. Yeah. So the Euler flow, no, the flow generated by Euler equation does not meet meets vorticity of V even in the limit. And I know I have to somehow denote N with the set of generalized minimal flow. Now, my claim, because it is partly definition, partly statement, is the following. N is V structure or spherical equation in weaker. This is what I am going to define, in which sense it is attractor, and not the last thing that it is non-trivial. First, and is not empty, No, for example, any stationary flow is here. If it is stationary, nothing changes. Second, and it's different from all the space, the Dirichlet space. This is maybe the least, no, the most non-trivial statement, which I will discuss it later. If such, and three, that V of T goes to N in a weaker sense. Not only weak, but even weaker. No, okay, we have what we have. So, and now I concentrate on this. What does it all mean? No, let me forward construction. Visualize minimal fluids. Construction of generalized minimal flow. How we construct generalized minimal flow? Consider U any element of Dirichlet space. Any element of Dirichlet space. Let us consider orbit of U and the closure of this orbit. Now we have two possibilities. Let us call V0. Suppose there exists U1 in the orbit of U0 such that norm curl U1 L2 less than norm curl U0 in L2. If such, take any U1 satisfying this so that its vorticity is a little bit more mixed. Yes. If such U1 does not exist, take U1 equal to 0. So I am constructing some sequence. Now, we have this U1. Define U2 in orbit, closure of orbit of U1. Similar way. If norm curl U2 less than suppose there exists U2 such that norm curl U2 less than curl U in L2. then take this U2. Otherwise, define U2 equals U1. And so on. So we defined this way n for any finite n, any integer n. Now define u omega omega 0. Omega 0 is in this case the first infinite ordinal, namely the set of all integers. As we point.
I have a probably quite naive question.
Isn't it?
I mean, that the fact that U2 is in the orbit of U1,
Yes.
I mean, implies as well this U2 is in the orbit of U0, no?
No, I don't know.
Close.
Maybe this, maybe not.
But it's, I mean, in the closure of, I mean, one is in the closure of the other, no? Because
I'm
O of U1, the closure, I mean, every point in U1, O of U1 I can approach by points of O of U0, no? As close as I want.
maybe I'm not sure. Currently, I'm not sure. You know what? This is the.
I'm only asking, let me just say why I'm asking it, because then otherwise it would be to me that I'm just taking a minimizing sequence.
You know what? I tell you. The Udovich space in which we work is not separable. It is like, no, if it is L infinity, it is not separable space.
Yes.
Yeah, so this means that the Euler flow in this space is everywhere discontinuous. So your intuition is intuition of continuous. So the Euler solution in this space, a solution can be defined individually. Yes, the trajectory can be defined individually.
But not uniformly.
It is depends discontinuously on the
Initial
initial
data.
condition. Yes, it is a first thing. This means that this limit passage can be not successful when you your picture is good for continuous flow. And here flow, it is an unpleasant situation with Euler equation that solution in some spaces depends discontinuously on initial condition. Yes, and anyway, my construction works not only in this situation, but in much more general setup, where again we can be not able to transpose these different limit passages.
Okay, thanks.
Yes, so with limit point of the sequence UN and natural. Such that no curve u on the 0 and 2 less than no curve u n and 2 is such u omega 0 exists. Or otherwise, any point u omega 0 in the closure. Any weak point. So if we can find some limit point with a mixed, which is more mixed than all of these terms in this sequence, then we take this point. Otherwise, we take no what remains, any of them. Yes, or yes, any point. And now we continue this process further. Continue further to find u omega 0 equals 1 and u 2 omega 0 on. So anytime we take u k, where k is any countable ordinal. It is what may be called the long sequence. Long sequence is a sequence which is defined not only for indices, natural numbers, but for indices ordinals. No, depending on what you need here, it takes all the countable ordinals. So u k plus 1 belongs to or UK by the above rules. Yes, so if there exists UK plus 1 such that its vorticity and L2 normal vorticity is strictly less than for UK, then you take this UK plus 1. Yeah. Otherwise, if such thing does not exist, we take UK. Yeah. And if say M is limit ordinal. Limit ordinal means ordinal which does not have predecessor. For example, omega 0 is limit ordinal, the first infinite ordinal. So we don't, there doesn't exist omega 0 minus 1. Yes. Then define work. Um as a with limit point of the sequence u k less than m such that norm curve u m into less than norm uk L2 for k less than n. K grows. If such um exists, or otherwise um is any element of weak load. No, not with closure. Any weak limit point. U k less than. And now I want to use formulate. Let me define. So we this way we define u k k k all countable ordinal. K less than omega 1, the first uncountable ordinal. So we define this signal and define also a k equals no curve UK L2. So AK more equal than 0. No, if energy is if energy is positive, energy is all the time the same. A plus 1 k less than m means that a k k less than m more or equal to m. Yeah, so it is non-decreasing positive sequence defined for all countable ordinals.
Sorry, why is it positive?
Positive because the energy is the same, and so by the inequality that to norm of u is less or equal than to norm of curl u. Yeah. We have that, and to norm of velocity is energy. So energy is positive. Yes. And now, no, doesn't matter. It can be even non-negative. It can be no. It can be A. Now the following lemma, which is simple, but I think it is powerful. Let's M B sequence of positive and positive numbers, which and be non-decreasing. Non-decreasing sequence of positive numbers defined for all and omega 1, the first uncountable ordinal, first countable for all countable ordinals. Then like this. I, J, K, L, M, let it L. Some countable ordinal. And that A, M, N equals A, L for all N more than L. The sequence that arises for N more than L. So the sequence not only goes to some limit, which we know from analysis, from all of the analysis, but somewhere it becomes constant.
Do you mean non-increasing?
Excuse me?
Non-increasing?
Non-increasing. Yes. For non-decreasing, it is also true. Yes. For yes, for non-decreasing is also true. Let's see. So why it is true? Yes, please.
Because otherwise you could construct uncountably many disjoint intervals on R.
Yes.
And then this is a contradiction, so it must end somewhere.
Yes, exactly this. So we have if n more than n plus 1, this means that there exists R rational number such that n more than r more than n more than r more than n plus 1. Yeah. And it is for ordinary ordinal, yes, and for limit ordinal, the same. If k is limit ordinal, and k less than there exists rk such that there is a limit yeah, so the sequence goes to some, and this is AK. And here continues the decrease. So, no, in other words, the set of jumps is countable, not more than countable. Yes, and the set of countable ordinals is uncountable. So this means this contradiction. So starting from some point, this sequence is non-decreasing. What does it mean? It means that if you consider if A, K, A, L for all K more than L, more than equal, yeah, then AK equals curve UK. And so then UK are very linear flows. Yes, because we cannot going along the trajectory, the vorticity does not mix. We know this criterion of mixing. After mixing, through mixing, the into normal function decreases. So this is why it happens.
Sorry, I have a basic question. If we have a vector field in geodesic class,
Yeah,
does it mean vorticity for finite time or only for infinite time?
infinite. Well, yeah, there's a strong theorem that vorticity, that solution exists for infinite time. If we are in geodesic class.
No, I mean not existence, but mixing. So if we fix into normal vorticity,
It is mixing in the limit.
yeah.
Yes, it means that on finite interval it does not mix. Only when we jump to the limit point, weak limit point, it may be mixed. And then from that point we can move and maybe we can jump to some further limit point.
Ah, I see.
Yeah. So we have this situation. Now, no, this is the way how we construct solutions. construct the generalized minimal flows. It does not say that they are in the limit. The set of generalized minimal flows is attractor. Yes, it is maybe a little bit artificial way. So to make it more realistic, we have to change the notion of dynamics. Notion of dynamics. So to this end, we have to extend the time axis. So I defined what is called Alexandrov line. It is what or Alexandrov or Long. What is Alexandrov line? No, it is consider omega 1. No, you know, in notations of set theory, each ordinal is identified with the set of all ordinals which were before it. Yeah? So say 2 is in set of 1. 3 is the set of 1, 2, and so on. So omega 1 times 0, 1 Alexander line equals omega 1 times 0, 1 with the geographical order and order topology. No, in other words, if we have element of this, K tau in Alexandrov line, yes, no, we can write to equals K plus 4. Yeah, so it is semi segment. Then so it is K plus 1. Here is next segment, and so on. Yeah, so K K1 is less than K2 2 if either K1 less than K2 or K1 equals K2, so 1 less than 2. Yeah, so we take all the semi-interval, put them like here. So the first point here in place of the absent point on the previous semi-interval. Yes, and after that we define in this linearly ordered set, define the order. And we define our solution now the following way. We take, say, u0 here, no, k 0, 1, 2, and so on. Here we define our first solution. Tau is not time. Yeah, here notate say time t equals 1 over 1 minus tau. Yeah, here on this chart. And here we write, no, simply we assume that this is half line. Yeah, so t is half line, no, say like this. Then we define here solution everywhere here. Here we take u0. Here we define it as u1, u2, and so on. And here we define it, no, say u 4 equals what it is, 1 over t equals 1 minus 2. T is so equals 1 minus 1 over t. Yeah. 1 minus 1 over t. And this way we define the solution here. Let's say, so here we have this some set of say moments where we use some arbitrariness, some arbitrary choice, because we have to choose some element weak limit or some subsequence. Yeah, this corresponds. No, you know, if you will not be too afraid, I would say that this is close reminds me what was proposed by I think by Epicurus in his description of the world dynamics. At that time, when Epicurus was alive and created, no idea of dynamic did not exist. Yes, so his the idea was for Democritus that everything is made of atoms. Atoms are moving, and what else? How to describe their motion? And Epicurus proposed they move, like balls in free motion, yes, but from time to time they suddenly change their position or their direction, make a small changes, which called Klinamine, this change. So this Klinamina is are elements of arbitrariness in their motion and their trajectories. So they bring, he was concerned, of course, with free will. So this Klinamina bring about free will. Maybe he added this free will of whom, maybe of gods and so on. But here we have also Klinamina. So in this long time, in this long time, the trajectory is not unique. Because we have infinitely many moments of free choice. No, what to do? We have to live with it. And what is important here, returning to our dynamics of the fluid, that starting from some point here, we have one and the same motion. One and the same, one moment. At least we have a motion along we have reached this set n. Yeah, so we are moving somehow, and when there is a set n, and we not only approach closer and closer to this set, but we are actually on this set. And since then, we are traveling along this set. Yes, and since we are keep using the same operation, the same when you jump over this point, the next ordinal, we have to every time we have to choose arbitrarily some point. No, we have this non-uniqueness. So I call this way this object middle evolution. It's evolution in the extended time. Does it, what relation this evolution or pseudo evolution has to the true evolution? It is not so trivial question, because I explain what is time. Time is measured by a sequence of events. Events are no in our model of life linearly ordered set. If the time is long, as happens, for example, with the Earth atmosphere and ocean, they live in a long time, then we have actually so many events that can we can regard as infinite set of events. And this set can have a different order structure. We have many different orders in infinite set. So which order structure is better to describe it? No, even when we describe, say, what we see in our numerical simulation, if we see some complex behavior, maybe this pseudo evolution is a better description. I don't know. But anyway, what is proved here is that if you replace our classical evolution but pseudo evolution, then eventually we will reach this would be attractor, the set of generalized minimal flows, and remain there. This is the result. I would say that this easy part, the difficult part will be if we prove that it happens here. Yes, we start and we don't need to go through all this long line, just in the ordinary line. But it is far from far from certain. Yes. Now, the next thing what I want to show you. How can we know that this set is not all the space? Yeah. Actually, we have to prove that the mixing, at least no asymptotic mixing, really happens. So we need some good example. Yeah. Fortunately, this example appeared recently. It was, well, let me write it, call it Landau density. Maybe you have heard about this thing. Landau damping for the Euler's equation. So consider possibly the simplest, but the same time maybe at the same time really tough example. Correct flow. It is a very concrete example. X1, X2, 0, say L. It is a periodic strip, yes, and U of X1, X2 equals X2, 0. So it is parallel flow with linear profile. And omega equals 1 part du1 dx2. Yes, omega identically 1, vorticity, identically 1. It is a stationary flow, and what can be said interesting about this? No, in fact, there is best literature about the properties, say about its stability in different setups and so on. And in particular, what the following, consider small perturbation of this flow. So this means that here vorticity is 1, and we write, let's call it U0, and vorticity number 0. And take U1 equals U0 plus epsilon d, and omega 1 equals 1 plus epsilon epsilon omega epsilon c. Yeah, c is and this perturbation. This what is this c? Say it is c in 0 infinity. No, for example, has the form of small of such smooth vorticity spot. Yeah. So now let us write the equation for omega 1. D omega 1 dt plus u1 times number omega 1 plus gradient P equal, no, gradient P equals 0, and U1 equals 12 minus 1 of omega 1 equals this familiar thing. And now P omega 1 P plus U0 U0 plus epsilon no V curl minus 1 of psi omega 1 dV 1 plus epsilon psi plus U1 U0 plus epsilon curl minus 1 of psi times number omega 1 omega 1 1 plus epsilon psi equals so epsilon d psi dt plus U0 number of 1 is 0 number psi plus now here psi times W0 psi U0 number psi plus here curl minus 1 of psi times nabla of 1, it is 0. Plus epsilon square, no, we take epsilon square equals 0. And now d psi dt plus what it is x2 0 times nabla psi psi 1 psi equals 1 d psi dx2 equals 0. It is linearized. equation. Or with psi dt plus x2 with psi dx1 equals 0. No, oh, that is simple operation. So what is it? Give psi dt plus x2 with psi dx1 equals 0. Psi x1 x2 equals psi x1 minus x2c x2 0. So this linear flow just basically transports this perturbation psi. Yeah. So and what happens next? Instead of this round spot, it will be, and this is periodic structure. We have the following. We have a narrow, long and narrow split like this. Yeah, because this flow will distort. It is the flow happens on the surface of side surface of cylinder. Yeah, and so it transforms this round spot into the this very elongated, twisted, no, not twisted, but coiled many times, like this. And so, if you consider evolution of this under linearized equation, then it really weakly tends to the averaged initial perturbation psi of 0. If you take average over x1 in this direction, yeah, then it will be the limit of this solution. So we write that psi of x1, x2, t weakly tends to integral of 1 over L, what is the length of this period, integral from say 0 to L, psi of x1, x2, 0, dx1. Yeah. And so what we will have? We'll have after knowing the limit and the weak limit, we'll have the flow, which is also a parallel flow, but its profile will be a little bit changed. No, for example, something like this. Yes, a little bit changed. This size is of order x. Very good. It's very good, but here are also nonlinear terms. And these nonlinear terms can spoil all the picture. And they turned out to be rather nasty, no, mathematically, and lead to the following phenomenon, which I can draw here. So we have here this very elongated thin strips. Yes, this is the configuration after a long time of our perturbation. And then because of these small terms, they form some secondary flow, which makes the following. It takes the piece of this and makes like this. No, I exaggerate. Yeah. So a little bit turns this picture. And what happens next? And next we have a powerful flow, initial flow, quiet flow, which will further quiet flow. Just imagine that its vorticity is positive, so it will further develop this perturbation. And what will happen next? Next, we'll see something like this. Yeah. And then it keeps rotating, yes, and forms something which looks like the initial perturbation. Maybe not perfectly. It will there will be some other structures, secondary and tertiary structures will be formed. This is what the people like Villani call it was this phenomenon. First of all, this theory was started in the study of kinetic equation of plasma. Yeah, in one-dimensional plasma, in some approximation, it is described by what is called Vlasov-Poisson equation, and where we have similar feature in the phase plane, and this is called echo. So this means that we introduce a small perturbation, then this perturbation, a small and localized perturbation, this perturbation then develops and like this, so it appears to disappear in some sense. This a little bit changes this profile, and then it recurred like this. So now you have also a spot of perturbation of vorticity. Yes, so it looks like echo. It was predicted, I think, by Landau, no, maybe by somebody else also, and it was observed in physical experiments. Some about 20 years after its prediction.
But it's because of adding of higher order nonlinearities or higher order expansion into
Yes, yes, yes. We take there's quadratic terms, and these quadratic terms they produce this picture. And in the Euler equation, quadratic terms are much stronger than in the Vlasov-Poisson equations. And so it is much tougher. Yeah, first, Villani and Moore proved that we can avoid this overturning if we are the perturbation is small and smooth. So in their work, if the perturbation belongs to vorticity belongs to not vorticity, they had the distribution function belongs to some algebraic class. Then if you do it very accurately, then such overturning may be avoided. Yes, so this job of let's say skewing this spot, it slowly becomes perturbations of velocity becomes smaller and smaller. Yes, because this is vorticity, and if the frequency it grows like time, so the amplitude of perturbation of velocity decreases like time, so it is becomes weaker and weaker. So we can avoid it. So it was done first by this Villani and Moore for the Vlasov-Poisson equation, and then in 2015 appeared the work of Bedrosian and Masmoudi, who established it for the Euler equation exactly for this. So the result is the following. Suppose that psi is in the algebraic class with some index, I forgot its bounds for this index. Then they were able to prove this also this statement that such overturning does not exist. We can avoid this overturning. Yes, so this making a coil is weak, it is slow, but it can be sufficient to avoid this overturning. In fact, yes, and what is the conclusion? So if you consider this initial condition, u zero plus epsilon v, where v is small in Geodesic norm, then the result will be the solution would weakly tend to another parallel flow. It is a weak limit, and the for this weak limit, the L2 norm of vorticity of this weak limit will be strictly less than for the initial vorticity. Yeah. So here vorticity, this is also if you consider these transformations for when t grows, then we have the actual mixing of this vorticity when t goes to infinity, mixing of the perturbation of vorticity. So it will. So it is example. What it is? It is example of U1. Example of initial condition such that it does not belong to is not a generalized minimal flow. Yeah, it is not a generalized minimal flow because if you consider its orbit, then somewhere in its closure, big closure of this big orbit, there is a point where the L2 norm of vorticity is less. Yes. No, in this case, it simply weakly tends to some stationary flow, so even simpler. But in general, the picture is no. In fact, I have this picture, but I cannot hear this. This picture, you can see it and let people see it. What happens if we have this overturning? It is a result of numerical simulation. Yes. No, that's it. So this means that this how to call it, very weak attractor really is non-trivial. What is the nature of this attractor? No, I have some hypothesis, but maybe it is premature because I also had hypothesis that minimal flows from this attractor and it turns out wrong. So I think here we will have a lot of surprises. That's it. It's what I wanted to talk to you. Next time we will consider some very different topics. Yes, from given. So we finish this mixing. No, okay. There are some speculations, but maybe I will not proceed. Okay.